It's my pleasure to introduce today's speaker, Nicholson. I've known Ru for, well, I guess by now it's becoming for a long time, and I've been following his career and his, sort of exploring and adding to Bayesian inverse problems in a lot of different contexts. And I'm looking forward to his talk today on linear surrogates in Bayesian inverse problems. And I also have to say that I'm very grateful that Ru accepted our invitation to speak, because being in New Zealand right now is the middle of the night. And Ru, it's all yours now.
Right. Okay. So Daniela, thank you very much, and to the whole panel. Yeah, thank you very much for the invitation and the opportunity to talk. It is kind of the middle of the night, but it is the morning, right? So I feel it's all good for me to say good morning to everyone as well. So good morning. It just happens to be Thursday morning here. So good morning from Thursday. So there you go. So today I'm going to be talking about, well, this evening, I'm going to be talking about the use of surrogates. So the use of surrogate models or reduced order models or approximate models in Bayesian inverse problems. And I'm going to pay particular attention to the use of linear surrogate models in Bayesian inverse problems. And so this is joint work with quite a few people, but the kind of main collaborators at the moment are Noemi Petra at UC Merced, Umberto Villa at the Washington University in St. Louis, and of course Jari Kaipio, who is recently back at the University of Eastern Finland, but who was at the University of Auckland, which is where I am. Okay, so hopefully that slide's changed now. So a little bit of an overview. So I'm going to give a very perhaps crass motivation, so very abrupt and quick and dirty motivation, and then a quick review of inverse problems in the Bayesian framework, look at kind of handling model discrepancy in the Bayesian framework, and in particular the Bayesian approximation error approach, and then kind of look at one example of kind of using a nonlinear surrogate, so a nonlinear reduced order model to approximate a more difficult nonlinear model, perhaps. And then we'll get into kind of what happens for linear surrogates. And I'd just like to say that I have also been following some of the talks that have been going on through the Imagine program. And so some of this was actually very briefly touched on when Jari gave his talk a little while ago, and he said he could give a whole talk on modeling the approximation errors, which was just sort of one little epsilon or E in his slides. And he said, I'm not going to spend my time talking about that, but I could. And so this is perhaps that talk or something similar to the talk he could have gone on to give about those modeling errors. Okay, and then, so yeah, as I say, we'll look at the linear case. So the case of linear surrogates, and then consider two examples, and then of course wrap up with some conclusions. Okay, so as promised, here's the very short version of a motivation. So I believe everyone in the audience is happy or accepts that inverse problems are everywhere. So we're going to consider, fairly standard problems of this form throughout. But of course, it could be more general. But so we're going to say that we're interested in some quantity of interest, and we have some indirect measurements. And as everyone knows, essentially always those measurements are corrupted by noise. And then it's becoming very much accepted that it's useful to be able to quantify the uncertainty and also to accommodate uncertainty. So accommodate the uncertainty we may have up front, and then to quantify the uncertainty we have afterwards. So after we've incorporated our data or taken into account our data, and that kind of leads naturally onto the Bayesian framework where we end up kind of having a posterior rather than the prior, and I'll talk more about, a posterior rather than just a point estimate, and I'll talk more about that in a moment. But also in many situations, there's a whole lot of other things going on that we don't know about. So we have some other parameters that are that are unknown, and if we accept the kind of Bayesian paradigm, then if something is unknown, then it should be modeled as a random variable. So we have other random variables or other parameters in the models, which we're often not interested in. So we don't even really care about those parameters. All we're kind of interested in are those, parameters of primary interest, I guess, which are going to be denoted by M throughout this talk. So if we were going to do everything kind of perfectly, what we would want to get is the marginal posterior, right? This thing here, but that's kind of overkill in most situations because we've had to compute the joint posterior already, right? This quantity, and then we marginalize out, and then so we get just that marginal posterior. But all we really want is to go directly to this marginal posterior, so that we don't have to kind of compute that full joint posterior. And so generally, solving Bayesian inverse problems is hard, and we would often like to do it in an easier way. So that's another motivation of why people would use surrogate models, is just to kind of make things easier, and that may be theoretically or conceptually, but also particularly computationally. Right, so surrogates are often used to kind of accommodate these two things. So one, we want to kind of ignore some of the parameters that are not of interest. And then we'd also like to often come up with a computationally cheaper model to help us solve the inference problem. Okay, so a quick recap of the Bayesian framework for handling inverse problems. So as I've just alluded to, anything that's unknown is treated as a random variable in the Bayesian framework. So that could be, for PDE style models, it could be boundary conditions, it could be the shape of the domain, which we'll get onto shortly. But so anything essentially that's unknown is treated as a random variable, and then the solution to the inverse problem is then the posterior distribution. So the kind of general idea or setup that we'll be considering is we have the data and we have the model. And so this model is kind of the most high level model we're having at the moment. So this this thing is kind of the set of all other uncertain parameters that we're not interested in. Again, we're only interested in this parameter here. So M, and so Xi kind of embodies everything else that's uncertain that we're not interested in. Okay, and so Bayes' theorem or formula or rule can be, well, it's often expressed like this, and this is fine for the finite dimensional case. And for ease of telling the story, essentially, I'm going to stick to the finite dimensional kind of framework, though things generally work out in infinite dimensions as well. And if people are interested more in the infinite dimensional framework, feel free to look at particularly this paper by Andrew Stewart. But generally the problems that I'm looking at, although the parameters of interest, yes, they are infinite dimensional fields to begin with, we usually discretize them using finite elements or some basis. And so what we actually end up for is an inference problem for the coefficients of those basis functions. So it all boils down to a finite dimensional inverse problem again. The only thing that one needs to be careful of really in that situation is making sure that we're working in the right kind of spaces. So often what comes up is kind of weighting inner products by mass matrices and things like that. Okay, and so there's some very good references and very standard references on inverse problems in the Bayesian framework. And so throughout my slides, a lot of the kind of main references are given at the bottom of the slide. There's, of course, many more references, and I apologize to anyone who's watching it that I don't reference your work when I should. Yeah, so there is a lot of good stuff out there on Bayesian inverse problems. The 3 papers at the bottom, or the 2 books and the paper at the bottom, are very good ones. And so Bayes' theorem or formula again gives us that the posterior is proportional to the likelihood and the prior, or the product of the likelihood and the prior. And so the prior encodes essentially all beliefs we have prior to, or all beliefs we have about the parameters, or anything we believe about the parameter prior to kind of considering the data. And the likelihood essentially gives us a way of incorporating that data. And it's generally thought of as a function of the parameter once the data is actually measured. And then again, the posterior is what we're actually after, right? So that's the conditional distribution of the parameter given the data. Okay, and so just as I said at one point, so the most high level kind of model we have is this, but in particular, we'll choose a specific example of that, which I alluded to earlier, where we have just the kind of so-called additive error model, where so this would be just the noise. And so the full set of all the other uncertain parameters is the set of kind of, we'll call them the auxiliary parameters, denoted by B, these parameters here, and then also the ever-present noise which corrupts the data. So in general, the noise is not independent of the parameters, and that's kind of a kind of key idea actually when dealing with the kind of model error or approximation errors that we're going to consider in a moment. But often people assume it is, and that's if it is independent of the parameters, great, and if it's not, well, of course that should be modeled. So yeah, so we're going to assume that we have additive noise, and it's not generally, or it's not necessarily independent of the parameters. And then again, these auxiliary parameters are not of interest, and so we'll talk more about that shortly. Right, so essentially just kind of applying Bayes' theorem now that we've kind of set up specifically what our model is, so our relationship between the data, the kind of the so-called forward model and all the parameters, and that we have an additive error model. Then we kind of just plug things in, so plug and chug essentially, and then we get that marginalizing over the error to calculate the likelihood. We see that the likelihood inherits the distribution of inherits the conditional distribution of the noise given the parameters. And so again, if the noise was indeed independent of the parameters, we would just simply drop this conditional dependence here, right? And that often pops up as well. And then again, just plugging in the kind of final step there for the posterior, we'd get that the joint posterior is given by that equation. So not necessarily normally, but assuming normality, here we're going to assume that for simplicity, really, that the prior on these parameters is normal, and that the distribution or assumed distribution on the noise is also normal, right? And I've just made a bit of a substitution in here, just saying that U is the set of all the unknowns, and Z is the set of just, well, so U is the set of all the parameters, and Z is the set of all the unknowns, so the parameters and the noise. in such a case, we have, so the key things here are that the likelihood is going to be of this form, and the posterior is going to be of this form. Okay, and so a couple of things that are not always present in all the literature is this term here, which is just the conditional mean of the noise. And this is just the conditional covariance of the noise. Okay, and so often it's kind of just assumed that this is 0 and this is independent of the parameter, and we would get that. But in the more general case, they should be retained. Okay, so that's kind of the crux of setting up the Bayesian inverse problem. And so solving the inverse problem or the inference problem, right, it becomes an inference problem, a problem of statistical inference. So there's various ways to solve such a problem. The accurate way to solve it would be to use Markov chain Monte Carlo or ABC. Usually ABC is kind of restricted to stochastic simulation models, but so there are accurate ways of solving it, and there are proofs saying that, you know, that given an infinite number of samples, we can accurately characterize the posterior using these methods. But typically what's done just for speed is to solve these problems approximately. And two of the more common approaches are either variational Bayes, which I will not talk about, or kind of constructing a Gaussian approximation to the posterior, which is often, so there's a large number of choices of Gaussian approximations to the posterior one could take, but one of the most common is the so-called Laplace approximation. And that's kind of what I'll be focusing on, and it's actually a slight variation on the Laplace approximation. So as I said, so I'll look at a Gaussian approximation to the posterior, and so that will be a Gaussian centered at the map estimate, which is defined as the point in parameter space which maximizes the posterior, and then the approximate posterior covariance matrix is going to be given by this expression, where this bold F here is now the Jacobian of the forward problem with respect to the parameters. Okay, and so typically the map estimate is calculated as a minimization problem, right? So we take, rather than maximizing the posterior, we typically, so sorry about the typo there, we typically pose the problem as minimizing the negative log posterior. Okay, and so so that means we kind of have two tasks. One is solve the optimization problem to calculate the map estimate, and then the second one is to kind of approximately quantify the uncertainty, which is based on a kind of local approximation, which we see by seeing that the posterior has the Jacobian in there, which is essentially taking a linear approximation to the forward map. Right, so as kind of said up front, we're only kind of interested in a subset of the parameters, right? We're only interested in M. And so in the Bayesian framework, we'd only be interested in that marginal posterior. And so just again, what do we have to calculate? We have to calculate this map estimate, and we have to calculate this posterior covariance matrix, and the space that we have to do that over. So once we've discretized the problem, is in a fairly large space typically, especially when these parameters come from discretizing infinite dimensional fields in PDEs. Okay, so once discretized, the space is this big, but computationally and perhaps conceptually, it would be much easier to solve if all the unknowns, or the only unknown was M. All right, so computationally, this results in a much kind of smaller optimization problem, and we may not have to compute some of the derivatives. So, I mean, actually by pen and paper, we wouldn't have to compute some of those Jacobians, so that would also kind of conceptually make things easier as well. Okay, so if we accept that it would be much easier to solve this problem only for M rather than for all the unknowns, M and B, it's tempting to just consider a setup like this. And I'm sure a few people in the audience are kind of familiar with this argument and know where this is heading. But so here we're just saying that G is essentially an arbitrary model at this point, but we're saying that it's not dependent on the auxiliary parameters or the parameters which are not of primary interest. Okay, and so for example, those auxiliary parameters are just fixed at some nominal value. It may be 0, it may be some physically well justified value or anything, but it is a value. And so then the map would be defined similarly to the map previously, but essentially we would just change this forward model, and rather than the joint prior term, we just have the marginal prior coming up. And then the posterior covariance matrix, well, taking this kind of local Gaussian approximation, the approximate posterior covariance matrix would be in this form, where G now is, G is now the Jacobian of the surrogate or approximate model with respect to the parameter of interest. Right, so the kind of main problem with that is that, again, in the Bayesian framework, this auxiliary parameter B, if we don't know it, it's a random variable, and as such, it's uncertain. And so, as has been demonstrated in multiple papers, and in fact, we'll go over an example here, if one does neglect the uncertainty in the auxiliary parameters, one does so at their own peril, and this generally leads to extreme overconfidence, or at least some overconfidence in heavily biased estimates. For example, the truth is generally not contained within the posterior anymore, which is a real issue and essentially says that the approach is not feasible. Okay, so one way to kind of take into account the uncertainty that using this reduced order model induces is to use the so-called Bayesian approximation error approach, which has been used quite a bit in the literature, which was first kind of employed and kind of written down and made a thing by Erkki Samasalo and Jari Kaipio. And has since been used by many people. And so in this approach, we can essentially account for, or approximately account for anyway, the model uncertainties. And one of the real benefits of this approach is at the online stage. So once you actually have the data, this approach leads to no additional costs. And one of the other kind of main benefits of this approach is that it doesn't really change the form of the problem. We still just end up with an additive noise model. And as you'll see in a moment, this noise is often or generally approximated as Gaussian. And so it doesn't really make any of the optimization or anything like that any harder. Okay, so how does this whole thing work? So the first kind of big assumption is that that the original model was accurate. Okay, and so that is an assumption. But so given that assumption, then this mathematically is fine, and all that's changed here is we have this term, which is generally referred to as the approximation errors. And so that's the difference between the models, right? And so mathematically, nothing has changed. Right? We've just added and subtracted the coarse model from the accurate setup. So this is exact. And then if we take the sum of all the errors, so the approximation errors and the kind of just additive noise that was in the models, and we set those equal to, just using eta here, and so they would be the total errors. So the approximation at this point is generally made such that we approximate the conditional distribution of the total errors given the parameters as Gaussian. Right? And as such, as we've discussed, the likelihood inherits the noise of the errors. So incorporating these model errors updates the likelihood. So again, you can see that it's of exactly the same form. It's just that the weight on the norm, so the covariance changes, and the shift or the kind of conditional mean of the errors is changed. Right? And because we've updated the posterior, this also leads to an updated, because we've updated the likelihood, this also leads to an updated posterior. So the unfortunate kind of part of this approach is that the statistics of the approximation errors cannot be computed analytically, generally, a priori. So what is done is they're typically computed offline. So this is before one collects any data using Monte Carlo simulations. And so there's some more, I'll talk a little bit more on that shortly. So what does that involve? So we would just take an ensemble of samples or a bunch of samples from the joint prior and run those through the kind of two models. So it's almost like a training phase. And so then we have a whole bunch of kind of samples of the approximation errors, and then we can just use the sample statistics for the mean and the covariance. Okay, so here's kind of our first example, but just as an aside, well, before we just get into this example, so the BAE approach is being used in a large array of applications, so from biomedical imaging to glaciology, and various geophysical applications as well, and things like process tomography and lots of things. Okay, so here's a kind of first example just to kind of see how things work. So if we consider this problem, which is motivated by sort of corrosion detection, so this may be either kind of thermal testing or non-destructive testing using thermal means or thermal tomography, or it may be electrical impedance tomography kind of setup. Not often used for corrosion detection though, just because hooking up electrodes to metal things usually doesn't give you too much information about the corrosion and things. But so we could imagine that this is kind of, we heat this up from below, from on top. So we put some heat flux in the top, and we're interested in the kind of admittivity of the bottom boundary as a kind of proxy for the kind of shape that this thing is in, as in, you know, is it corroded or not? In this case, we're not considering that the boundary shape changes with the corrosion, but that could also happen. Here, the corrosion is all explained by this Robin coefficient, essentially. But also, in essentially all cases, the conductivity, whether that's thermal or electrical, of the specimen or the body there would also not be known. So that again would be another parameter. And so we're going to say that we're not interested in that conductivity. And so we're going to go ahead and solve this using FEM. So just a quick recap. So we take measurements of the temperature, say, at these locations. We feed a thermal flux through the top, take measurements at those locations, and try and estimate the admittivity of that bottom boundary. Okay, and in this particular example, we're interested in that Robin term and not in the conductivity. And so this is a case where you get quite large computational savings if you ignore the uncertainty in the internal conductivity, because if you were to estimate the internal conductivity, it's a three-dimensional entity, whereas the thing you're actually after, that Robin coefficient, is just a two-dimensional parameter. And so you kind of have the number of unknowns is substantially less if you ignore the uncertainty and the conductivity. So we'll just consider kind of three cases here, just as a comparison. So first, as a kind of reference case, what happens if you actually did solve the inverse problem using the true conductivity? Then what happens if you kind of just set the conductivity to some nominal value and solve the inverse problem and forget about the uncertainty or modeling errors that induces? And then what happens if you do take into account the additional uncertainty using the BAE approach? All right, and so just kind of this is the kind of setup. So we generate, some samples from the joint prior. So in this case, there was 1,000 samples, and that would give us everything we need to compute those the second order statistics of the approximation errors, and that gives us enough to form the likelihood and consequently the posterior. And you can see this is the sort of standard behavior one gets. So here's the true, this is the kind of the beta coefficient, or the Robin coefficient on that bottom boundary. And then this reference case was when we had the true conductivity used in the inversions. And so it's a very good estimate, and that's great, and it should be. And then if we neglect the induced uncertainty, this is the estimate we get. All right, and just for kind of visualizations of the uncertainty as well, I've plotted the estimate and the approximate posterior credibility intervals or error intervals below on those two cross sections. And we can see that if we don't include the uncertainty induced by not knowing the conductivity, the standard approach, so the blue here is the truth, and the red is the map estimate. You can see that the map estimate, although qualitatively it's got some of the same behavior, it's not very, quantitatively it's not very good. And it's especially bad when one considers the associated uncertainty estimates, which are these intervals here. We can see that the truth is essentially completely outside the posterior, which essentially says that the truth is impossible. On the other hand, if we do include the approximation errors using the BAE approach, the map estimate is not too bad. It's been pulled towards the prior a little bit, and we can get into that a little bit later perhaps. But again, the map estimate, is quite good, and we see that there's kind of substantial increase in the uncertainty estimates. Because it's incorporating this uncertainty in the conductivity, right? And we can see that this posterior is essentially completely feasible in that the posterior contains the truth very well, right? And just for reference, this was also the kind of prior uncertainty. Okay, so that's kind of how the general kind of Bayesian approximation error approach works. And that's in that case, we had that the coarse model was actually essentially the same model, just with the fixed conductivity. So I've said that the coarse model is essentially arbitrary, and we'll talk about that more later if there's time. Right, so as I said in the last example, we basically had that the coarse model or the surrogate model was essentially the same as the accurate model, just with a fixed conductivity. So we were just using it to kind of pre-marginalize or marginalize over the uncertainty in in the conductivity. We can also kind of use it to kind of reduce the dimensionality of the problem, but not only the forward problem, but also the dimensionality of the parameter itself. So that can actually induce some uncertainty. So often people take sort of KL expansions or things like that and truncate. That can actually induce some significant model uncertainties. We won't look at that here. But one of the kind of extreme cases perhaps is taking a linear approximation to a nonlinear problem. All right, and so then we just get a linear inverse problem and things become very straightforward. Okay, and so that has been done in various applications. So there's a couple of references down there for applications, but some of the more recent ones are using the Born approximation for scattering, and we'll get into that soon. But also people have, I mean, the most common one perhaps is replacing a nonlinear map with the kind of Fréchet derivative of the forward problem, and that's kind of something that was considered in this paper. So something slightly more involved was done there, where the approximation errors were actually were made more and more relevant because they were kind of computed over better and better estimates of the posterior rather than over the prior. But that's another discussion for another day. Okay, so we're going to be particularly interested from this point out in using a surrogate model, which is essentially just a linear mapping, so a matrix. Right, so the coarse model is arbitrary, but of course, what happens is if we do have a very poor choice in the surrogate, we have excessive or very large modeling errors, right? And so essentially we get the signal is essentially just swamped by modeling error. And as such, we get that the kind of updated posterior essentially just starts heading back towards the prior, which is actually not a bad property in that, I mean, one would kind of hope that, right? If we had too much noise, basically the data doesn't tell us anything. Okay, so in terms of the linear case, so just some notes here that this is all kind of possible in the infinite dimensional case, and in the infinite dimensional case, we would, you know, be considering G a mapping between, or linear operator, bounded linear operator between some relevant spaces, but we can just think of it as a matrix for now. So how does one choose a good kind of linear surrogate? So typically, as I've said, these are based on sort of asymptotic arguments, or such as a derivative, or expansions about some point, or something like that. And so for example, yeah, the Fréchet derivative in electrical impedance tomography, and so that was, as I said, that was used in this paper, and then also things such as the use of the Born approximation for scattering. So one other option we could choose as another particular choice of linear mapping is the zero model, right? So that's just, you give it some parameter and it just maps it to zero. Right, that's linear. Initially, it doesn't seem like a great choice, and we'll talk about that in a moment. But one of the benefits of this is that it's completely hands-off. Right? I don't have to do anything. So if I choose my coarse model to be that, I don't have to worry about writing down anything, and I don't have to worry about computing anything in some sense. So I would still have to compute the accurate model to learn the kind of difference between the accurate model and the zero model, but I wouldn't have to run the coarse model because I know the output is zero. So it turns out, and so for some people this may be intuitive, but for me it certainly wasn't. And I'm not sure if this is in the literature, this is something we kind of came up with. So the likelihood is invariant to the choice of linear model one chooses. Right, so in kind of, here it is in all its kind of formal glory. So if we have some nonlinear mapping, right, and so this is a mapping of both parameters now. Right, so that's the kind of accurate nonlinear parameter to observable or forward mapping. Then the likelihood is, so if we consider the likelihood kind of parameterized by the choice of linearization, as long as we take into account the approximation errors using, for example, the Bayesian approximation error approach, then for any two linear mappings, so any two bounded linear operators here in the kind of most formal sense, then the likelihoods are equal. Okay, and that's actually not, I don't think the proofs are here actually, but it's essentially just a linear algebra argument, and it's not anything too involved. So just to kind of demonstrate this, we'll kind of consider two examples that are very similar to some examples that have been looked at in the literature. And so one of those is the inverse scattering problem or transmission problem. So in the literature, it was slightly different. They looked at the case of far field data. I'm going to use kind of so-called near field data where we actually have kind of some measurements around the object rather than computing the far field data. And so in the literature and in this, well, no, sorry, just in the literature, they spent some time computing the Born approximation. And so just a very brief side note is that Jari Kaipio was one of the authors on that paper, and he's also one of the main collaborators for this project. And so afterwards, after that paper was published and we kind of were talking about this, he was a little bit disappointed in the fact that they had spent so much time coming up with and computing the Born approximation and all these things when they could have used nothing, right? They could have used the zero model. But okay, so we'll look at that example, and then we'll also look at another example where we're going to have some additional unknown parameters which we're not interested in, and specifically we're going to consider the boundary shape as unknown as well. For a kind of EIT problem, it's a little bit different than the one in the literature, but it's again based on an actual sort of Fréchet derivative in the literature, and I'm going to compare the use of the Fréchet derivative and the zero model. Yeah, so as I said, so in both of these cases, we'll use the zero model. So first up is the scattering case. So a very kind of standard problem, so a classical inverse problem. So we're going to assume that there's an incident wave coming in. And of course, the total wave can be represented as the sum of these two fields, the scattered field and the incident field. And the parameter of interest here is going to be the refractive index. All right, and just kind of if you work through these things, if you say that the scatterer has, you know that the scatterer lies in some region, then you can say that the refractive index is 1 outside that region, and so then Q is compactly supported, and we kind of end up with this problem. So we're only considering the two-dimensional case. So that's the problem for, this is in terms of the total field. And we have the kind of summer field radiation condition. And then so we can actually just turn this into solving a problem for the scattered field, where the right-hand side is kind of dependent on the incident field. And just as an approximation for the kind of to compute it in a finite size domain, we're just using this sort of 0th order absorbing boundary condition, which is essentially just a Summerfield kind of looking. So this is at infinity, sorry, but in terms of actually computing it, I would just implement a this style of boundary condition on the finite domain as well. And so we'll consider a so-called multi-static setup where we have, we can control the direction of the incoming incidence fields. So we have a bunch of incident fields coming in from all different angles around the scatterer, and we measure at a bunch of locations around the scatterer, and we just take pointwise measurements. Okay, and so here we, just like in the literature, we've generated samples of the parameter. So this is the scatterer, or sorry, the refractivity index. This is what it may look like. So these are samples from our prior, but then actually we're going to do, well, we're going to consider a more complicated example, because the Born approximation, as we may be familiar with, is only good generally for kind of single scatterers, but also for low aspect ratio or low ratios between the background and the kind of scatterer. And so we're going to consider a kind of high aspect ratio scatterer, and we're also going to consider something that's in the shape of a resonator. The added difficulty here is that the resonator is not kind of, you would never expect to get that from the prior, right? The prior is just made up of, as you can see, it's made up of samples of ellipses. So 1 to 3 ellipses with random refractivity. Okay, and so what does this look like? So here's, as I was saying, here's the resonator. So this is the truth. Here's the particular wavelength that we used. And so this is just looking at the convergence in the number of samples. And so for a low number of samples, so this is just with 10 samples, you can see that the estimate, the map estimate is essentially meaningless. But you can, some interesting things there is you can see that it's kind of made up of a combination of, or projection down onto the kind of 10 samples there. And then as we increase the number of samples, so if people don't want to read the caption, so this is 100, 1,000, 5,000 samples, 7,500, and 10,000. You can see that by the end, it's looking pretty good. All right, and so this is in slightly different setup, but in comparison to this result from the literature, and we can see that it's I mean, essentially the same, and further numerical experiments showed that yes, it had converged by that point. Okay, so that again, that was with there was no linear model there. It was just generate samples and compute the conditional statistics of the conditional mean and the conditional covariance matrix. Okay, and so here's the kind of convergence of the approximate posterior as well. This is along the cross section here, PQ, and you can see initially the estimate is bad, but also the uncertainty estimates are terrible as well, and that's just because when computing the conditional covariance, we have an inverse of the prior covariance matrix, and that prior covariance matrix used should be the sample covariance, and so when we only have a few samples, that inverse becomes a pseudo inverse, and it doesn't give a very good estimate. But we can see that as the number of samples increases, we get better, not only better, conditional mean or map estimate, but also better and more accurate uncertainty estimates. So again, that's the same number of samples. So that's 10, 100, 1,000, 5,000, 7,500, and 10,000 samples. Okay, and then the final example is it's loosely based on a variation of the continuum model for EIT. So we're going to consider the kind of standard problem where the conductivity is unknown, and we're just ensuring it's positive by using the exponential mapping. But also we're going to assume that the boundary of the domain is unknown, but not of interest. We're just interested in the internal conductivity. Excuse me. And so for simplicity and for lack of imagination, we essentially just choose that the boundary can be parameterized using Fourier basis functions, so it's star-like. And again, these coefficients here would then make up the parameters which are not of interest, but they are uncertain parameters. All right, and we're going to consider pointwise measurements around the boundary. We consider 16 different kind of current patterns, and we're going to compare it to, we're going to compare the two approaches of A using the Frechet derivative and B using the zero model. Okay, and so here's kind of the samples from the prior. This is what they look like in this case. So again, we sample the Fourier coefficients and we sample the conductivity within it, and so we get samples where the boundary shape is uncertain, but also the internal conductivity. And so here we're just using some sort of Wood-Matern style prior covariance matrices for the conductivity. And so here's kind of the comparison of the map estimates. And so these were both computed using 10,000 samples. So this is the truth, and this is the truth projected into the circle. And then this was computed using the Frechet derivative, and this was computed using the zero model. And you can see that the map estimates have essentially converged to the same thing, and that the posterior uncertainty down here, so this is the corresponding posterior uncertainty, has also, after this number of samples, they've converged to the same thing, kind of verifying, even though there's a proof, it's always good to just show kind of numerically with examples, just verifying that yes, indeed, it doesn't matter which linearization we choose. Okay, so one of the issues here though, and which was not stated, is the theorem is only asymptotic, right? So it was based on knowing, the proof is based on knowing some of the covariance matrices, but you can only compute those accurately if you have an infinite number of samples. So what happens if you take the zero model as the linear model? Well, then it essentially just takes this as the approximation errors. And so then we need to compute the conditional covariance and mean of that. On the other hand, if we take some other G, so some other linear model, then we need to compute the approximation errors of this quantity, right? And for a G we choose, then we can compute analytically and a priori the covariance of this term, which leads to the idea of using it as a control variate, right? So we can actually use it or think of it as a control variate, which means it generally reduces the number of samples needed to compute the mean and covariance of this quantity. Okay, and we can see that in the uncertainty estimates from the previous example. So this is for 10, 100, and 1,000 samples. And so the first one is using the zero model, and this is using the Frechet derivative. And you can see the estimates look almost identical. They are not identical, but you can see that the uncertainty is less pronouncedly underestimated using the Frechet derivative. Again, these still look different at 1,000, but they do converge after 10,000. Okay, so that's kind of it. And so some concluding remarks. So as is hopefully well understood by most people, that if you have model errors or model uncertainties, you should at least try to take these into account or model them. The Bayesian approximation error framework provides a fairly straightforward means to do this. Essentially, it involves a for loop before you do the inversion. And so then, yeah, using a linear surrogate can speed things up a lot, of course, because it results in a linear inverse problem. And then this is perhaps a not so standard way of saying, so one should not spend too much time figuring out a good linear surrogate, because that time could have been spent just running the accurate forward model, right? And that's all that needs to be done if we use the zero model. So if one has handy a good linearization, such as a Fréchet derivative, go for it and use it, and that's good. It'll be better than the zero model in terms of you would need to run less models to compute the statistics, but you shouldn't spend too much time trying to figure out a linear surrogate, because all that time you could have just been running the accurate model, constructing the statistics of the approximation errors based on using the zero model. And then finally, all linearizations are equal if we could take enough samples, and sometimes we can, and so that's fine. And with that, I thank everyone, and I'm completely open to questions.
Okay. Well, thank you very much. This was a very, very interesting, exciting talk, Rook. And are there comments or questions from the audience? I'm gonna. You have a question?
It looks like Erky has his hand raised.
Yeah, I'm gonna.
Do you hear me?
Yep. Yes. Hi, Jari.
I'm not sure if you hear me. Do you hear me?
Yep.
You do hear. Okay.
Yep.
Yeah. So thanks for this was. Sorry, just a moment. We have a little bit of echo. Yeah. All right. Yeah. So thanks for this was really interesting, and I was impressed. I've been talking with Jari about this idea of using a zero model, but it was kind of a joke, and now you have shown that it actually works. So this is great. In some sense, I think that what you have done is some sort of Bayesian neural network, in the sense that you are giving the data, but you are not using a model, and still it does a good job. And so you're sort of doing the training using this error model. And the other comment that I have is that if you have a, let's say, less ill-posed problem, let's say X-ray tomography, then probably the model becomes important. So the ill-posedness somehow helps you, because it's easier to capture the features of the modeling error with let's say few random draws from the prior when the problem is ill-posed. So I wonder if this zero model works if you use it, let's say, if you look at the X-ray tomography.
Yeah, so a couple of things on that. One is, there's definitely information loss, right, with the ill-posedness of the problems, and I do think that kind of helps. It does, given an infinite number of samples, right, it's provable that it doesn't matter which linearization you use. So I guess I agree that the zero model is going to be, it's never as good for a small number of samples, and depending on how good the linearization is, that would depend, or that would kind of dictate how few or many samples you need. So for a problem that's essentially or almost linear, then if you have a linear approximation of it, which is a good one, then this this idea here, so the use of control variates can reduce the number of samples dramatically if you have a very good so-called control variate, which in this case would be the linearization. So I haven't applied it to X-ray tomography, but I know that's a very, very well ill-posed problem. So that would kind of the proof would be in the pudding then, just to explore that and apply it to that problem. But again, I'll just emphasize that, given enough samples, it must perform as well as any other linearization.
Thanks.
Trying to handle two computers into small space here. Okay. So, yeah. Other questions from the audience? If not, let me thank Ru again for kindly giving this talk. And this was a very nice talk, you know, and in the middle of your night. So we're looking forward to seeing you in person
good to see
again.
Yes.
And take care. Thank you, everyone.
Thank you.